students, we are here at the conclusion of week 8, and it is Thursday the 27th. And I'm going to go again with a slightly different look here for this one. So what we'll do to start off is I'll remind you about PLC 8, which is again due Friday. Homework 5, I posted that and it is going on, posted, and that is for April 10th, which is after spring break. We come back, and spring break is the 1st, so 7th, 8th, 9th, 10th, so it's a Thursday after coming back from spring break. It's going to involve interference, it's going to involve polarization, which we are in the middle of finishing off, and it's going to involve instruments and compound mirrors and lenses, which we've already done. So we will probably begin interference today, and we'll have Tuesday when we come back to talk about that, and probably should be enough. Tuesday, Wednesday, probably be okay with that. We'll have our usual quiz on that day as well. And so that's what's coming up. Spring break is next week, so again, I encourage you to go have a great time. What we have here today is the conclusion of polarization and the beginning of interference. So we are thick into the wave behavior of light and examining some of the properties of light. So let's go ahead and keep going with that. I did the example in the last video of polarization, okay, and the idea that we have unpolarized light and polarized light, and we can make different types of polarized light. So what I've been doing is I've been representing the electric field vector as a line. So we've talked about linearly polarized light in the sense that we have something like this, and the electric field is oscillating in one direction. Okay. So if you continue to think of the electric field, and perhaps it's not just a situation where I have an up and a down, but I can have different components of the electric field. When we take unpolarized light and we shine it through a polarizer, then what we get is something that's going to be linearly polarized. Now, I can certainly take that polarizer and orient it in different directions, which is telling you that the unpolarized light has various spatial components of the electric field, and we can take advantage of that. So, since we have both X and Y components, X and Y components of the electric field, then we can use them and add them at different times when they have different sizes. Okay, so we can take something where, for example, suppose that I looked at a 45-degree polarization. All right, so suppose that I had a linear polarization, but at 45 degrees. That would mean that I would have, say Y is up and X is that way. So I would have an EY that way and an EX this way, right? And then what would happen is they would grow at the same time, and then they would shrink, and then they would grow this way at the same time, and then shrink, and then they would grow this way at the same time and shrink. So what you're having is basically a polarization, which is going, if I draw it in time along this way, right, and then there's a dot, and then maybe it goes down like this and over like that, and then the next one is down like that and over like that, right? So if my EX and EY change from being this to being smaller to being nothing to being this way and then being bigger this way, then what's happening
is that the initial polarization vector would have been this way, and now it's slightly less this way, and now it's nothing, and now it's slightly more this way, and now it's slightly bigger that way. So what's happening is I'm getting a linear polarization, which is doing that at 45 degrees. I also could take these and I could have them hit their maxima at different times, right? This is the case in which they're both maximum at the same time. What if they were not maximum at the same time? Well, in general, I would get, let's say that they are maximum at 90 degrees time, right? So that I have them out of phase by 90 degrees. Well, let's do this. So that I'll draw it out first. So I have one going this way. So my EY, say, is that way. When EX is 0. And then in the next point in time, I have this going this way, and I have this going this way. And then I have nothing this way, and then EX going that way. And then I have a little bit this way and a little bit that way. Okay, so what's happening, this is EX. So what's happening is the polarization vector is actually, so it's initially it's following this, and now it's going here, and now it's going here. I'll just write in another one here. And now it's going here. Okay, like so. Can you see it's actually rotating around in a clockwise manner? This would be known as left circular Is this the right or left circular polarization? This must be right circular polarization. Oops. Oops, I guess I'm just writing circular. Circular polarization. In which I'm making it go around like a clock. I think that is left circularly polarized, and if I went counterclockwise, that would be right circularly polarized. Nonetheless, I can have the polarization rotate, and it becomes a circle. So this one ends up going around like this. Or I could have it go the other way and have it go around like this. And that's circularly polarized. Now, I could also have them reach their maxima at points that is not 90 degrees out of phase, so that maybe this one has a maximum EY, but EX is not yet. It's not 0 and it's not maximum. It's somewhere in between. I think maybe I can convince you if you go around and draw that, the next more general phase of this would be elliptically polarized. Okay, so we can get polarizations which then look like this, right? Or this, like that, right? Or the other way, going in opposite directions. So the electric field vector the tip of it can rotate around in time. And in fact, this is how 3D movies work. If you have 3D glasses, you have one polarization this way and one polarization this way, so that you're getting the sense of depth from that. Pretty cool. I'm going to show you a little bit about what's called birefringent materials. And we're going to talk about polarization by reflection. Okay. Polarization by reflection is known as Brewster's angle, or well, it happens at something called Brewster's angle. And I talked to you a little bit last time about polarization by scattering, which is that if you look up in the sky, you'll see a bright, which if you're wearing Polaroid sunglasses, you can make into a bright and dark region of sky as long as you're 90 degrees from the sun. And the reason is just because of how the dipole action of the radiation is when sunlight, or in general radiation, hits a scattering object like an air molecule. A number of them, right? A whole bunch of air molecules, they're all going to get together and they're going to radiate in a dipole sense. And it turns out that the electric field is a maximum along the line of sight perpendicular to the acceleration of the charges that are induced in the in the air molecules. So let's go ahead and take a look at polarization by reflection. This comes about because of materials. It comes about because of the reaction of materials to different polarizations. Okay, so what we can do is, and you may have asked this question of yourself, is how does a Polaroid work? How does a polarizing filter work? Why can I take these two like this? Why can I take these two like this and rotate this one? Let's see here. I can rotate this one, and I can get different amounts of light let through like this, right? So here we have cross polarizers, and here we have approximately parallel polarizers. The question is, how do these things work? Well, Polaroid, at least when they came out, was made of an interesting salt, a kind of an iodine quinine salt called, I don't know, some chemical name, like hepatite or something, I don't know. But the idea is that when you have materials, the materials can have asymmetric molecules, and the asymmetric molecules can react differently to different polarizations. So suppose, for example, that you had a material that had a bunch of long, thin molecules, right? So they kind of join together in a fibrous sort of way, like they join together like this, and you had more of them together like this, and they were maybe joined a little bit across like this, so you had this ladder effect going. Well, if I send in light that's polarized this way, and I send in light that's polarized this way, this material is going to react differently to these two polarizations. All right? So let's just suppose that, for example, this reacts very easily. It's easy, right? So that the index of refraction for this is relatively small, more like maybe 1.2 or something like that. But the index of refraction for this one will be different because it's harder for the charges to accelerate across this small little bond, whereas this way it's very easy to. Or you might think the opposite, maybe this is quicker. The point is that it's called birefringent. In other words, this type of material will react differently to different polarizations, and that means the material has a different index of refraction for different polarization light. Okay, so this is known as birefringent. Birefringent. There we go. Birefringent means different index for different polarizations. So we're finding that not only does the index depend on things like the wavelength, but it also depends on the polarization. The index is a very complicated quantity, much more so than we're making it out to be here. Suppose that we have a higher speed as in the wave as we send these in, lower speed when we send in these. That means this index is larger, this index is smaller, and that means that because of the propagation of the waves through the material, one polarization will travel faster than another. Suppose that the vertical one is traveling faster than the horizontal one. So right now it's unpolarized, say, coming into a material. Let's just suppose, what I'll do is I'll draw this on the board. Suppose that I have unpolarized light. I'm going to need more than that, so let's go here like this. Suppose I have a chunk of material here and I've got unpolarized light coming in. How do I denote that? I guess I denote it this way and then this way. The dot meaning it's coming out, and I can't put the X right on it, meaning it's going in, but suppose that I have light coming into the material at right angles this way, and the electric field is such that it's oscillating this way. We know it has to be perpendicular to the direction of motion, right? And also this way. All right, so that's what these two, that's what I mean by the up and down arrow and then the dot, like so, okay? So it goes into the material. Suppose that the vertical travels faster, okay? So it's gonna be oscillating. They're gonna be going up, down, up, down, up, down, up, and then they're gonna hit the material. And this one's gonna go up, down, up, and it's gonna be out, whereas this one's gonna go up, down, up, down, up, down, and it's gonna be, right? Now there's gonna be a phase difference between the two waves. In other words, if you think of it, I have these rods. Suppose that we have crests. Suppose we have a crest at each one of these white marks here. So the wave looks like that, and then looks like this, and then looks like this at this crest at the next white marker, valley here, crest up here, valley down here, all right? So if they're coming in and one of them has a polarization that is traveling quicker than the other, okay, so they come in, they're in phase. Suppose the lower one is traveling slightly slower than the upper one. Let's see if I can get these to match up relatively well. Right, here they come. They're traveling in phase. They hit this, but this one kind of travels, and then they come out. You see now that they're going to be out of phase. The upper polarized one, which was vertically polarized, this one is horizontally polarized. There's a difference in the wave. There's a difference in the phase of the waves now. That's what I'm trying to say. So now notice that a peak here, a crest of the wave, is now matching up with the valley of the other one. And so these two waves might be destroying as you come out, right? They're going to be out of phase by a little bit. Well, not 100% destroying, but nearly. Okay, so that's called birefringent. And when you have reflection off a surface, actually, before we get to that, let me show you this. Let me show you this demo. Actually, no. Let's go ahead and do this. Let's go ahead and go back to this. So when I have polarization by reflection, what that means is unpolarized light is incident on a surface, okay, and some of it's going to reflect, and some of it's going to refract into it. It's transparent material. Now, depending on the polarization and the preferences of the molecules that make up the material, the reflected light will be polarized in a plane which is parallel with the surface of the material in some conditions. We'll talk about the conditions in a minute. But can you see that makes reasonable sense? I talked about what happens when it goes through the material here. I didn't talk about what bounces off, okay? But can you see that the same type of thing might be happening if the material reacts more favorably to a particular polarization? Then when that polarization hits the material, it's going to go, and it can reflect that, because ultimately all reflected light is the interaction of the incoming light with charges in the material, who then go, I'm going to oscillate with this frequency of light, and then they're going to oscillate, they're going to accelerate, and they're going to re-radiate. Okay? That's all reflected light really is. It's just the bounce, it's just the reaction of electric charges within the material such that they emit radiation in a preferential direction. Okay? So the same thing's going to happen here. If I have a material in which the charges are easily moved, say this way, then if I shine only light that's polarized this way, then I'll get a nice strong reflection, right, of that type. If I put in polarization of light this way, I'm not going to get a very strong reflection. It will probably refract into the material, okay, but it won't reflect very easily because the charges aren't moving in a way to regenerate the electromagnetic reflected wave, okay. So it comes about because of the material that it has, the structure of the material that we're talking about. So let me see if I can do this. I doubt that I can, but I'll give it a try. So let's give this a go, and this is going to be a little bit janky, but they always are, okay? So I'm going to turn on a light. I'm having it shine on a block, of acrylic down here, and then I'm gonna take you down here and we're gonna look at it from a certain angle, and we're gonna rotate the polarizer and see if we can't detect the reflection components and their polarizations. All right. So let's do this. All right, so here you go. I'm gonna bring you down here. Okay, so we're gonna take a quick look at this from, say, this angle here. Well, that's not a great angle because that light is so bright. So maybe if I, okay, I didn't realize that was gonna happen, but let's see if maybe I do something approximately like this. Maybe that, if I can drape a little bit over the top of it, maybe it's not quite so bright and you can see into that. No, I don't think you can. I don't think you can see that. But nonetheless, let's give it a try. I'm gonna reach over here for a polarizer. And if you watch the reflection of in the brick from about this angle, maybe I can cut it down a little bit. If I rotate around, maybe I can cut it a little bit. Yeah, it's hard to tell. Hard to tell. Trying to see if we can just get that to. Yeah, you can see it's just it. Yeah, look at that. Look at the very middle of the brick. See, it's getting a little darker. Okay, I'm going to call that a success. That's your polarization by reflection. So, all right. So there's that. Okay. So let's talk about that. Let's let's get a drawing of that on the board here so that you can see what it's going to look like. Now, the polarization of the reflected light, okay, is going to be in the same direction as the plane of the surface. So what that means is, if I draw a surface like this, and I have a light ray coming in, say I have a light ray coming in like this, and it's unpolarized, say, that means I'm going to draw the same type of situation here, where I have an electric field vector bouncing back and forth this way. I have an electric field vector bouncing back and forth this way. Okay, so it's the same idea as before. It's coming in like this. Okay, and it's going and hitting the surface. Oh wait, whoops. I'm so dumb. It's got to be perpendicular to the direction of travel, folks. I got too caught up in. There we go. Okay, maybe that's a little better. Yeah, diagrams that don't work, that's not fun. So it's oscillating like this, and it's traveling that way. It's going to hit. We know that we would drop a normal onto this and say I've got an incident angle here, and therefore I have a reflected angle this way. Now suppose that this is the exact right type of situation here, where right, so I've got incoming light that way and outgoing light this way at the same angle. Call this theta capital R. We also know if this is transparent, then I'm going to get a refracted ray that's going to go this way. So the refracted ray, it turns out, is going to go like this. And I'm going to have this happen here. I'm going to call that theta little r. So I got theta capital R for the reflection up top, theta little r for the refraction underneath, and let's look at what the polarizations are. If this is what's known as Brewster's angle, all right, suppose that theta I is equal to Brewster's angle. Then what we can say is that the polarization of the outgoing reflected ray is parallel with the surface. The surface is this way, so the polarization that survives on the reflected ray is this way. that means I get this, right, as the polarization of this one, and that means I get this as the polarization of this one, like that. All right? And just remembering this has to be perpendicular, okay, in this one. When does this happen? This happens when theta capital R plus theta little r is equal to 90 degrees. And if you're hawk-eyed about that, what that means is there's a 90-degree angle right here between the reflected and refracted rays, which means that if there's a 90-degree angle here, then these two have to add to 90 degrees. Okay. So I don't know if I said this before, but it was a little bit of a lie, which is that every surface offers a little bit of reflection. Well, it doesn't, because if you have polarized the light properly, then you may not get a reflection. What if you polarize the light only this way? Well, then you're not going to get a reflected beam if you shine it at this angle, at the Brewster angle, because the only way you're getting a polarization is in this one down here, because this one only supports this way, right? So reflection doesn't always have to happen, depending on what the polarization looks like. Okay, then that's an interesting little piece. I also had a birefringent material here to show you, and I can try and do that, but my fear is that it will be the same as with the demonstration I just did. In other words, the light is so bright that the camera is getting washed out and dimming a lot, and therefore you can't see any of the details I want. So I had a great demo of a birefringent material, but I guess we're not going to have that. So maybe go find someone else on YouTube who's got one of those. But I'm thinking I'm not going to be able to do that. Okay. So we have the Brewster's angle, and we have the polarization by reflection. So that's basically polarization by reflection, and that is polarization of materials. Okay, so let's go on here. I think what we'll do now is we'll just go ahead and start hitting some interference. I think that's going to be enough of what we need with geometric. I'm going to do one other thing though. Before we do this, I'll do one other thing. I'll do a quick example of radiation pressure. We talked about this last time, so I thought up kind of an interesting example, and one that's a bit of an approximation, but that's okay. Let's do a quick example of radiation pressure. So radiation pressure, I thought about, okay, let's think about Earth. I talked about the solar sail last time, which is the idea that NASA sends up into outer space something that has a large aluminum foil, and then the sunlight bouncing off it starts pushing it because there's a momentum change in the light, meaning there's a momentum transfer from the light into the spacecraft with the sail. I thought, well, we are on a spacecraft right now, so let's talk about what the radiation pressure from the sunlight looks like in terms of a force exerted on Earth. The radiation pressure on Starship Earth. Now, here we are, and basically we offer a circular cross-section to the sunlight. Okay, so sunlight's incoming like this. So Earth, right, which is really spherical. If I think about the radiation that's coming to hit Earth, it's offering essentially a circular cross-section, and it's not 100% hitting dead on, right? So I might be a little bit off with the assumption that the radiation is perpendicular in and we're getting a full transfer. But nonetheless, let's make an approximation. Let's suppose that we assume Earth absorbs everything, okay? So sunlight hits Earth and gets absorbed, and there's a momentum transfer from the sunlight to Earth, okay? And that means that we're going to use the absorbing radiation pressure. Okay, so what this means is because it's absorbing, we're going to look at the radiation pressure, which I'll use a capital P with a small little foot on it to call pressure. And this is going to be the intensity divided by speed of light. Well, the intensity of sunlight at Earth's surface is fairly well known. This is at Earth, the sunlight is about a 1 kilowatt per square meter. It's a good number to know offhand because it's just one, and it also is good to know approximately how a kilowatt relates to a horsepower. So I will tell you that it's approximately 1. It's not, it's more like 750 watts to a horsepower, but nonetheless, it's about 1. So if you're going to approximate things, you could say it's a kilowatt per square meter slash a horsepower per square meter. So now you can maybe start to understand just from arguments about the size of this number, why solar powered cars are not really in our future. I know we have the solar racers because I remember this from back when I was in college. You get the solar panels, and you try to build the lightest, most sleek possible machine that you can make, because boy, a stiff breeze comes along and it stops these things. They don't usually, a 1 horsepower car, and you're talking for a square meter, you'd have a square meter solar panel on your car to get 1 horsepower. So that doesn't really track with American culture of more horsepower. So it's not really a thing we're going to be exploring, I think. But nonetheless, let's take a look at it in terms of the force exerted by the sunlight on Earth. So if this is the case, then I would say the force exerted is the pressure that's applied by the sunlight multiplied by the cross-sectional area of Earth, which, as I have said, is essentially circular. Okay. So let's just say it's approximately going to be the pressure, which is 1 kilowatt per square meter, divided by 3 times 10 to the 8 meters per second. Okay, so that'll be the radiation pressure. We're going to multiply that by the cross-section of Earth, cross-sectional area of Earth, which is approximately pi times, say it's about 6 times 10 to the 6th meters. That's going to be squared. So all of you who are laughing at the tiny itty-bitty radiation pressure because I'm dividing a number that's 10 to the 3 by 10 to the 8. So this is a number in the order about 10 to the minus 5. But now I'm multiplying by 10 to the 12. Okay, so this number works out if that's about 10 to the minus 5th, and that's about 10 to the 12th. So this is a number that's around 10 to the 7th newtons. So not bad, 10 million newtons pushing Earth just because of the sunlight. And yes, I mean, that's an approximation, sure. But nonetheless, it's probably somewhere in that ballpark. Why are we not simply pushed off track? Just by way of comparison, because this is what we like to do in physics, let's compare that with the gravitational force from the sun. That should be approximately, so if you know your Newtonian law of gravitation, G times m1, m2 over r squared. So let's go with G being about 10 to the minus 11. Mass of the sun is about 10 to the 30. Let's say it's about 10 to the minus 11 times 10 to the 30. And mass of Earth is about 10 to the 24. And I'm going to divide that by, what's the distance between them? It's 150 million kilometers. So that looks like about 10 to the 8th. 100 million should be about 10 to the 8th. Oh, that's kilometers. 10 to the 11th. squared. Okay, so one of those goes away with one of those, and 10 to the 11 leaves about a 10 to the 2 right here. So the force exerted by the sun on Earth is around 10 to the 32 newtons. So that's a little more, as it turns out. So we don't get blown off out into the nether regions of the universe. Oh, why don't we get pulled backwards straight into the sun then? Why are we not in a flaming part of the sun? Ah, physics. You know the answers to these. All right, so there's a little bit of radiation pressure. What I'm going to do now is we're going to go ahead and move on to interference of light waves. Okay, so the interference of light waves. I'm going to cut straight to the chase here and tell you there's essentially 3 ways that light waves interfere, and I say essentially, but this is not the end-all be-all here. This is for at least for our purposes. There's basically 3 ways in which light interferes with itself, or maybe, what would you say, another beam, something like that. All right, so let's take a quick look at this. Imagine that I had a source of light here, and it's emitting light, which is what I call monochromatic, single wavelength, right? One color. And what I'm going to do is I'm going to put it into, I'm going to have it hit a half-silvered mirror, which means it lets half of it through and half of it bounces off. Okay, like that. And I'm going to put another half-silvered mirror over here. And what I'm going to do is I'm going to say the light that comes in here, right, here comes incoming light, and it's going to get split. Okay, so half of the light's going to go this way. Half of the light's going to go this way. Right, so if this is 1, and it's a half-half. Okay, now I'm going to put another mirror over here, such that this is a much better mirror. This is a 100% mirror. Such that this bounces off here, and comes back and recombines with the original beam. Now, if we consider that light is made of wavelengths, okay, then we're going to run into an issue, because there's going to be a different number of wavelengths that are going to have gone up and down here versus here, here, and here. The question then is, when these 2 beams recombine here, what is the relative phase difference between the 2 waves? Okay, let me repeat that. What is the relative phase difference between the 2 waves? So if I say that this one's coming in and it's just going blah, 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 and this one's still going da, 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 and it would have gone da, 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 the entire rest of the way, this one is going to have traveled more wavelengths because it's a longer path, okay? And therefore, I want to know when this one hits this one, right, and they come back to recombine, where in their paths, where in their cycles are they compared to one another? Perhaps we can make this fairly interesting. Suppose that I have, say, 1 wavelength here. 1 wavelength every 4 of my grid spacings here. So if I do every 4 grid spacings, then I do 1, 2, 3, 4, 1, 2. Oops, wait a sec. 1 near. I did that kind of wrong. That should be. Yeah, that's right. 1, 2, 3, 4. 1, 2, 3, 4. All right, so it comes out like that. All right, so say it's hitting this mirror kind of at that point right there. It's at the, what you would call the half wavelength, or the pi mark, if you like. Whereas if I thought about this, this goes 1, 2, 3, 4. So this is a full wavelength here, a full wavelength here, but I got, no, it's a little bit off. So we'll go from here. So we'll go, and this path should be exactly the same to there. And now it's going to bounce one full wavelength here. 1, 2, 3, 4. Oops, wait a minute, sorry, that's wrong. It's going to bounce one full wavelength from here, which means it's going to start there and it's going to go under. So it's going to go under first, come back over, and then go there. Now it's at the same basic point as the other one, okay? So that what I did was I made this path one full wavelength. This path travels the same as this path, so there's no difference there. This path is also one full wavelength, so the phase difference is 2 wavelengths. But if I have a 2 wavelength phase difference, their peaks are still matching. Okay? In other words, if I go back to my interference sticks here, okay? Here they come into the first mirror like this, right? This one keeps going and reaches there. This one goes down, around, back up. And now what's happened is, because this took 2 extra wavelengths worth of travel, it's back here, like so. It's 2 full wavelengths behind. This is in phase, this is 1 full wavelength behind, and this is 2 full wavelengths behind. However, their crests still match, their valleys still match, and therefore this is called constructive interference. Okay? Nonetheless, the question remains, what is the phase difference of the waves when they meet each other? That's the answer. The answer to that question is what we're trying to find here. Okay? Okay, after they get back to that point, what's the phase difference between the 2 waves? So here I've demonstrated one way in which waves can have different phases when they recombine. And this is known as a path length difference. Okay, this wave just traveled a longer path. So this is called a path length difference. Simply having the wave travel different distances from another wave means that they will arrive back not at the same point in their waves, right? This one would happen to be 2 wavelengths behind. So whenever you have a situation where one wave travels slightly longer than the other one, there's going to be a slight shift in the waves relative to one another. Okay, so this is one of them. Another one that we're going to find is going to be a phase change, which is due to a different number of wavelengths traveled. And you'd say, well, wait a sec, how's that different from this? It's because when you go into an index, the wavelength changes. Okay, so this is one situation. Another situation would be due to or let's say a change in the wavelength. Okay, we could have a difference in the wavelength. So what that would mean, so this is one answer. Here's another answer. Here's another answer. I'm going to do the same thing. Monochromatic light source. I'm going to have 2 blocks stacked on top of each other, like this, but they have different index of refraction. Okay, so suppose that this one is N2, this one is N1, and let's suppose that N2 is greater than N1. Okay, what we're going to do then is we're going to look at wavelength number 2 compared to wavelength number 1 and ask, is it greater or smaller? Well, if you look back at this, well, let's do it here. If you look back at this fundamental relationship between wavelength and frequency for light waves. What happens to the frequency when it goes into a material is that the frequency stays exactly the same as it was. Okay, so in other words, it's still bouncing it's still bouncing as frequently as it was when it wasn't in the material. But the distance it goes is shorter. That means the wavelength has changed. Okay, so F is the same, and the wavelength changes. Therefore, if it goes into a material and is no longer traveling at c, it's traveling at speed, say, v, right? I'm going to put lambda naught here and lambda n here. The frequency is still exactly the same. And so if I divide these two expressions, what you notice is if I divide c by v, I'm going to get c over v. And I'm going to divide lambda naught by lambda naught divided by lambda n. And the frequencies are still the same, so they will cancel out, right? So if I just did a division of these two, this is what would happen. I would get that, which means that lambda n is equal to, if you notice that c over v here, this is actually equal to n. All I got to do is flip-flop those two, and I notice that lambda naught divided by n is the new wavelength in the material. So if I have a material which has a larger wavelength, then according to this, it will have a larger wavelength. If it has a larger index, then it will have a smaller wavelength, right? So if that's the case, if n2 is greater, then lambda 2 is less, okay? And that means even if they travel the same distance, there's a different number of wavelengths in n2 here than there is in n1. Then when they re-emerge this side and become waves in air again, what they're going to do is they're going to be at different places, right? Out here they're going to have the same wavelength again, but they're going to be at different places in their waves again. And so I'm going to get possibly an interference, okay? So due to a change in the wavelength, because it went through an index, right? A material with an index. Another one is due to reflection at a boundary. Okay, so down here I've got answers to this question due to a change in the wavelength. I'll put path length difference down here. This is one that we will explore at length. The path length difference. This pen can't spell. Okay, and the last one here that we're going to be talking about is reflection phase shift. So I don't have to put off a material, it's going to reflect, you know it's off a material. What happens is another situation with reflection. You thought reflection was so easy, angle of reflection equals angle of incidence. Not so easy, is it? All right, if I'm talking about something going like this, all right, here comes the wave. I'm going to draw a beam, but I'm going to put a wavelength on top of it. Okay, here comes the wave. All right, so it's hitting at the point in its wave where it's just finished the trough and it's about to start the next peak. When it hits this material, suppose that it has a higher index, such that the speed is lower in there, right? So if I get one in which the speed is lower, it's going to reflect off. This will be different from when the speed of the light in the material is higher, right? So this is the situation like I'm going from a material of index 1 to a material of index 2, all right? So when that happens, I get a reflection phase shift, and the reflection phase shift, let's see here. I just want to make sure I'm going to get this right because I always seem to mess this up. The reflection phase shift is such that, so if I'm going from a material of N1 to a material of N2, if N2 is greater than N1, then I get a reflection phase shift. If it's the other way around, I get zero reflection phase shift, which means that the outgoing ray, which would obey the law of reflection going that way, would have flipped over. So it was about to do a peak, but instead it's going to do a trough. So that means the outgoing wave starts with another trough and goes like that. Reason being, if it hadn't flipped, it would have been doing a peak right here. Okay, so this is a reflection phase shift. If N2 is greater than N1, then the phase shifts by pi. Or 180 degrees. It flips the wave over. If it's the other way around, then the phase shift is 0, right? So these are the three main pieces that we're going to be concentrating on in this class. We'll start off with ones due to a change in just the wavelength by itself. All right, so a situation like this, I'll do a quick example of something like that. All right, so let's do this. I'm going to take this out. Okay, so if I look at same wavelength light coming in, okay, call that lambda naught here, and then it's going to have a different wavelength, lambda naught out here. It's going to have lambda n2 in here. I'll just call it lambda 2. Lambda 2. This one's going to have like that. This is lambda 1. And so the question is, when they leave the material, what's the relative phase between the two waves? Because back here, they were swimming in phase. They were coming into the material going like this. Okay? And now one of them's going like this, and the other one's going still not more frequently. No, if they were going like this, then it's just going like this. Right? It's not going as far with each vibration. In other words, its speed has slowed down, which is what we expect. Let's suppose that we have a length L here. And we have an N1 and an N2. So what we're really interested in here is the difference in the phase out here. Typically, the phase difference, okay, I want to talk about the phase difference. How do we represent this? Well, we can represent it in a couple of different ways. We can represent it usually by saying how far out of phase one is from another with respect to the number of wavelengths. Okay, so maybe they're out of phase, like I did in the last example with the path length difference. Maybe they're out of phase by 2 wavelengths, right? You might say, well, they're out of phase then by 720 degrees. Or you could say they're out of phase by 4 pi. These are all equivalent ways of representing the phase difference. Hopefully it makes sense how I'm talking about it. So you can talk about it, and typically this would be something like delta phi, or something like that. It might be lowercase like this, or it might be capital. So you might talk about it as something like 2 pi times the difference in the number of wavelengths traveled. That would be delta n, which is the difference in number of wavelengths traveled. So that if I say, oh, well, it was different by 2 wavelengths, well, 2 times 2 pi is 4 pi, and then you'd know, oh yeah, that's 2 wavelengths, right? So it typically is either that, it's not so much the degrees, we don't typically use 720 degrees or something like that, but you would use, oh, it's 90 degrees out of phase, or it's 180 degrees out of phase. So if it's between 0 and 360, you can use the degree terminology. Or you can use the number of wavelengths, right? So 2 waves that are out of phase by 90 degrees are out of phase by 1/4 of a wavelength, which is pi over 2. I almost said pi over 4 because of the quarter, but no, it's pi over 2. So 90 degrees is pi over 2 out of phase, which is 1/4 of a wavelength, okay? So those all kind of go together. Hopefully that makes sense. And yeah, looks like it does. Okay, great. So let's calculate the difference in the number of wavelengths traveled here. So what I'm going to do is try to calculate what is delta n. So delta n here, okay, is going to be, well, you're going to look at the number of wavelengths here and the number of wavelengths here. So this is essentially L divided by lambda 1, or say lambda 2, because that's got more, divided minus L over lambda 1, right? This is just a straight number. How many wavelengths were in this much, right? I've got a wavelength of 3 and a distance of 12, oh, 4, right? So it's a number. We do know how to represent lambda 2 and lambda 1 in terms of lambda naught because we have the indices. We have the n2 and n1. So I can rewrite this, for example, as L divided by lambda naught times, okay, if I put in here, this is lambda naught divided by n2, that takes the n2 and flips it up to the top. So what I'm going to get here is n2 minus n1, difference in the indices. All right, this should turn out to be just a number because I'm still dividing a distance by a distance, and these are unitless because they're ratios of speeds, okay, or distances, or whatever you like. Okay, so that's basically how you would represent the change in phase. I could take that as the total difference in the number of wavelengths, or I could multiply it by 2 pi, or I could say it's some fraction of 360, however you like. All right. The point is that you can compare, for example, lambda naught multiplying delta n equaling L times n2 minus n1. Right? So it's the difference in time, it's the number of wavelengths different it is related to how far, how much the block thickness is divided by the difference in the indices. So what you'd say is if lambda naught times delta n is equal to, for example, 0, which we know it wouldn't be unless the indices were the same, or 1, or 2, or 3, dot, dot, dot. What that means is I'm taking my two waves, they're going in, and say, by the time they come out on the other side, they're shifted by, say, 2 wavelengths. But that means that the peaks still match up, right? If you look at these, the peaks still match up with the peaks, the valleys still match up with the valleys. And we call that constructive interference. That's constructive interference, meaning that you've built a bigger wave. To give you an idea of why it's called that, I can do a little bit of visual addition for you. In other words, if I take a wave that looks like this, and I add it to a wave that looks like this, what do you suppose we get? Well, the peaks are matching up, the troughs are matching up, so when I interfere, if I have 2 peaks matching up, I go up a higher peak. If I have 2 valleys matching up, I go down a deeper valley, and it goes up and down, and it's got a larger amplitude. Okay, the amplitude, as you probably are aware, is that distance there. Not from peak to valley, it's half of the distance from peak to valley. It's like peak back to sea level. All right, so if I add these, then I'm going to get this. Okay, same frequency, right? The peaks should all still match up, but the amplitude is now double. Right? If I call the amplitude A and I call this A, then it's 2A for the amplitude down here. All right, this is what's called constructive interference, and that's what would happen if you got the waves shifted by an integer number of wavelengths. If they were shifted by, say, a half, or 3 halves, or 5 halves, or something like that, I see that I'm messing this up a little because I've got a lambda in here. So I should do this. Times lambda naught, right? I'll do the same thing down here. Times lambda naught, okay? Like so. We call this destructive interference. And that's the situation where, okay, instead of adding two waves that look like this, I'm going to add them such that they are now a wavelength out of phase with each other. Or sorry, half a wavelength out of phase with each other. So such that one wave is at its peak and the other wave is half a wavelength out of phase. But if you look at what that means, if it's a half a wavelength out of phase with the other one, then it's doing this. Right? Now I've got a peak matching a trough on the very end. And if you look back at all of the rest of the pattern, okay, it's all off, right? It's all out of phase by a half a wavelength. If it's out of phase by a full wavelength, it's here. If it's out of phase by a half, it's here. If it's 3 halves, it's there, right? 2 is here, then 5 halves is here. So anything that's a half integer difference in the number is going to come out such that the peak that it starts with is getting added to a trough on the bottom, so it looks like this, like that, and I'm adding a peak to a trough and a peak to a trough and a peak to a trough. So what do I get out here is a big fat nothing. Okay, I have made this wave disappear. It is called destructive interference. Okay. If they are out of phase by something that's not either an integer or a half integer, then it's partial. Okay, it's either partial construction or partial destruction, however you like, whether your glass is half full or half empty. Okay, so that's what this looks like. Alrighty. So that being said, for this, let's take a quick look at throwing in a few numbers on something like this. So in that example, if the length is known, for example, and I have an N1 and an N2, suppose I have a delta N here, and I know that the lambda naught is some wavelength, like 500 nanometers, something nice and green, okay? If I say that I've got L divided by lambda naught times N2 minus N1, suppose that this is some number here. I just said maybe this is a block of something like, it's 50 times 10 to the minus 3 meters, and I've got wavelength of light, which is 500 times 10 to the minus 9 meters, and I've got, I'm gonna want to make that a little bit less. Right? Maybe make that 6. And let's say I've got a 1.7 and a 1.6. Okay? So what do we get when we look at these numbers? This top number is 5 times 10 to the minus 5. This is 5 times 10 to the minus 7. So this is turning out to be 100. And that's 0.1, right? So what I'm getting when I do that is 10. And that means it's out of phase by 10 full wavelengths, yet it's constructive. Okay? Now change it somewhat. Okay, suppose now that instead of having a 50 times 10 to the minus 6, it was something else that would have thrown the numbers off a little bit. All right, so let's suppose, let's see, I came up with something a little bit different for this one. Let's suppose now that it was something like 7 times 10 to the minus 6. Okay, so now this is not going to be 10. Right? This is going to be 7 times 10 to the minus 6 and 5 times 10 to the minus 7. So this is going to leave you with 7/5 times, 7/5 divided by 10. What did I say this was? 7 times 10 to the minus 6, 10 to the minus 7. No, times 10. Times 10. But that 10 is going to get taken away by that 10. So the wavelength difference is essentially 7/5. which is what, 1.4 or so? No. Yeah, it's going to be 2 2/5, right? Yeah, so it's 1.4. So now suppose that I've got that and it's equal to 1.4. What does that mean? Well, look, it's not 1, 2, 3, 4, so it's not constructive. It's not half, it's not 0.5, 1.5, 2.5, 3.5, so it's not totally destructive, but it's pretty close to destructive. It's closer to destructive than it is to constructive. So this would be dimmer, okay? So this is close, this is partial destruction. Okay. Okay. Let's move on to the double slit experiment. The double slit experiment is a great example of a path length difference. Okay. So a path length difference a path length difference is, remember, the situation in which one wave travels slightly quicker than slightly farther than another wave. Double slit experiment. So the double slit experiment is really nothing more than light shined through two slits, and the two slits are really small and they're pretty close together. Okay, so it looks like this. Here's my light source over here. Again, this is a monochromatic light source, so it's emitting only lambda naughts, right? It's a laser. Lasers emit single wavelengths, or at least reasonably well enough. I'm going to put these things through a double slit, which is to say I'm going to separate, I'm going to have two slits in this thing here, so hopefully you can kind of see I've got two slits there. Yes, you can. And I'm going to have a screen to catch this pattern on over here. Now, in the same way that we talked about geometrical optics, I'm going to talk about small angles in this case. I'm not always going to draw small angles, but we are going to talk about the small angles, because what's going to happen here is that when the waves come through here, right, what we find is that they spread out like ripples on a pond. If you just drop a rock into a pond and you watch the wave pattern, that's basically what it looks like coming out of these slits. But they're so close together that if you drop this rock here and this rock here, and now you're looking at the interference pattern between the two waves on the surface of the pond in the ripples. So I have a kind of a picture of that. I don't think you're going to quite be able to see this too well, but suppose that I have these two sources that look like this, and then I move. No, you can't see that. All right, so there you go. What's going to happen then is they're going to travel different paths. Okay, so if they travel straight, then their path length is not different. Okay, I'll call this distance d from slits to screen. That's typical. Now, if they travel and I look, now because remember they're like ripples on a pond, they're going in all directions, right? They're radiating out here in all directions. So I can choose a direction like this and find out what's the path length difference if I go at an angle now. If I go at an angle, then I'm going to go like that with one of the waves, close enough for government work, and I'm going to go like this with the other wave, like that, and I'm going to say, well, I can see they're kind of curving upwards at the end there. Oh well. I say, well, past a certain distance, they traveled all the same amount. The question is, what's the distance extra that the lower one did that the upper one didn't do? And it all happens right here. Okay, so let's just blow this up. I'm going to show you, here's the slit. Okay, so here's the upper slit and here's the lower slit. Now, this is a wave traveling out like that. This is a wave traveling out like that. They are essentially, remember how I said the angles were pretty small? They're essentially parallel here. Of course, they're intersecting over here, so they're not, but they're close enough So what we're going to do is say they're essentially parallel here, so I can form a little triangle. I'm going to form my triangle by saying if I drop a normal from the top one to the bottom one here, that is the extra distance that the lower one has traveled, because after that they went the same distance. Okay? So this right here is the path length difference. That's it right there. And if you know how to get that and what that means and how to calculate this, then you can 100% figure out every problem to do with the double slit experiment. Okay, so it's all about that little bit right there. This is a triangle, and I know we love triangles. Let's put a hypotenuse in over here. This is a right angle because I dropped a normal. Let's call this distance right here, call that little d. That's the distance between the slits. I want to figure out what this path length difference is, so I'm going to ask what's this angle, theta. That angle by geometry is going to be the same as this angle right here, theta. So my path length difference here is going to be equal to d times sine theta. In the approximation that we're talking about small angles, then since theta is small and it's got to be in radians, okay, if you're doing this type of thinking, typically you don't calculate anything on a calculator in radians, you're using thinking to do this. So in the small angle approximation, what we're going to do is we're going to say that that angle is so small, theta is much less than 1, remember radians, that the sine of theta is approximately the same thing as the tangent of theta. And that's the same thing as the angle itself. If you look at the Taylor expansion of the sine, then what you'll find is the first term is theta, and the next one is theta cubed over 3. So the next correction to this is a cubed in a small quantity, which is basically negligible. Okay? So the question is, what's the tangent of theta? The tangent of theta then would be, for example, this distance here, call that y. It's y divided by capital D, because this angle of the triangle is the same as the angle of the rays coming out of the slits. So if I'm looking at that angle, that's it right there, then the tangent is y over d, and I can use that as an approximation to the sine of theta down here. Okay? So this is approximately little d times y. I'm going to put the little d later so you don't think it's a differential in y. Like dy would look like a small dy. It's not that. It's y over d times little d. Okay, the entire question comes into how many wavelengths do we fit into this tiny little space? If we fit an integer number of wavelengths, then guess what? We've got constructive interference. If we fit a half integer of wavelengths, guess what? We've got destructive interference up here. How do we tell the difference between constructive interference and destructive interference if we're talking about light? If I add light to light and get constructive interference, that would be a bright spot. It's known as a fringe. Okay? We talk about them as fringes. So this looks like a bright fringe right here if this is constructive. If this is destructive, then it's a dark fringe because you have canceled all the wavelengths. Okay? Therefore, what happens when you shine light through two slits is you get a pattern, all right, a bright central region with dark spots or dark fringes, and then bright fringes, and then dark fringes, and then bright fringes, and then dark fringes. Basically, it's a two-slit interference pattern. All right? If I were to draw for you with the intensity on the screen, what it would look like is, right, these two waves are in phase when they hit the central point here. So I'm going to get a lot of light right there. Okay? Lots of light right here. But notice now it's dipped down to 0. Because at this distance, right, at this angle of the light rays, of the light waves, they're going to be destructively interfering. So I'm going to get no light there. Then I'm going to get a pattern where I'm going to get a construction again. And I'm going to get a construction again. And then I'm going to get a destruction again. right? And so this is what and I don't know if that looks, it is a little bit higher. It should not be a little higher. It should be the same size as the central, so it should go like that, right? So these are all kind of lined up. I got that one a little bit lower. That one should kind of come up a little bit, all right? Okay, so that is the pattern of the double slit experiment. You find that there are bright spots or fringes and dark fringes. These are bright fringes, right? Bright fringes. And these are dark. And again, same thing, dark fringes. Okay, so what we'll do next time is relate the path length difference to an index, which tells us whether or not it's an integer number of wavelengths, or a half integer number of wavelengths, or something in between, right? So essentially what we're asking is this path length difference equal to some integer, m, right? 0, 1, 2, times lambda naught, in which case it's going to be a constructive situation, or is it, say, m plus a half times lambda naught, in which case now I've got a destructive situation, okay? So, constructive, this is destructive. All right, so if you are able to understand, A, how the path length difference comes about, B, how to calculate it, and C, what's the relationship of the number of wavelengths that you fit into the path length difference that determines your the type of interference you have at that spot on the screen, then you can fully understand the double slit experiment. This is simply a path length difference and nothing else. I see that we're about out of time for today, so what we'll do is on Tuesday of the second week of April, so not next week, the week after that, we will pick up here with some examples of double slit interference, and then we're going to go to, we've done the wavelength one, this is the path length difference one, and then we'll do the reflection one. So we'll do a couple of examples of double slit, we'll get into reflection, and we'll go from there on Tuesday of next week. So stay tuned for lab, which is coming on Friday. And other than that, as the class instructor, I'm signing off until a week from next Tuesday. Happy spring break, everybody. Be safe out there, and I hope you enjoy your time. Do some physics, and enjoy looking at the world around you. And until next time, happy days.